2, 1. Not too much movement. Hello world, it's Siraj and welcome to this live stream. In this live stream, I'm going to be talking about Node.js, and we're going to be using machine learning for that. So the code is going to show up behind me when I move it. So it's going to show up. I'm just setting up some live things right now. It looks like the code is not behind. There we go. Okay, cool. All right, so, okay, I'm so excited to be here. Thank you guys for coming. So we have a lot to talk about today. We are going to build a Node.js app from scratch. And this app is going to be able to translate in real time. So check this out. Here's a translation demo. Okay, let me make this a little bigger. So this is in real time. This is what's happening, okay? I can say, how are you? And it's going to translate it in real time into French. So English to French translation in the browser immediately. I can say, hello world, it's Siraj, and then it's going to say, you know, whatever it needs to say. Okay, so that's the demo that we are going to build today. This person is saying my left ear is highly educated. Well, guess what? Your right ear is going to be as well because there's no audio in the left ear. Okay, we're going to fix that. We're going to fix that for you. Okay, so stay on. We're going to fix that for you. In the meantime, let's get right into this. Okay, so what I want to do is just say 5 names and then I'm going to start coding this. Okay, so Amanpreet, Silly, Tian, and Martin, and Deepak, and Rishit. Okay, and then the question, I only see one question. Have you ever loved anybody? Yes, it's called my community. It's called you guys. That's why I do this thing. Okay, so let's make everything big, and now we're going to look at this. So I'm going to talk a little bit about what Node.js is, and then we're going to talk about how machine translation works using sequence-to-sequence models, and then we're going to code this thing out in JavaScript, okay? All right, so let's get right into this. So Node.js. So JavaScript was initially invented just for in the browser scripting. It wasn't made to create standalone applications, right? So you wouldn't build a model that allows for requests to be coming in JavaScript. And JavaScript wasn't made initially to handle a bunch of concurrent requests, you know, like for post requests, for data, etc. But the developers of Node.js said, you know what, let's create a JavaScript runtime environment. That's an entire environment that you can use JavaScript to create standalone web apps. And since then, it's kind of exploded in popularity. Look, Node.js is not a new technology. It's a relatively you know, in programming terms, it's an older technology. It's about 5 years or more older, but it's a very good technology, and we can use it. We can combine it with machine learning for some amazing results. So if we look at the analogy of Java, so most of us are familiar with Java because Computer Science 101 classes teach Java generally, and if you're not, that's okay. But basically, what I'm trying to show is the analogy of what Node runs on, and it runs on what's called the V8 engine. And V8 engine was created for C++ specifically, but you can use it with JavaScript now. And what it does is you type in JavaScript in the browser, and it compiles it down to very fast machine code that's readable by your machine. Okay, so no longer is JavaScript just constrained to the browser. You can use it for all sorts of things. Okay. Nice audio for you. Fix the audio. All right, well, it's fine now. Okay, so the other thing about Node.js is, if we look at the official Node.js website, let's look at the official Node.js website, all right? Node.js is a JavaScript runtime engine built on Chrome's V8 JavaScript engine. And what it does is it creates an event, and here's the key right here. It creates an event-driven, non-blocking I/O model that makes it lightweight and efficient. Let's break this down. I/O means input, output. This can be anything from reading files, writing local files, making an HTTP request, right? Anything that you are inputting into a model and then you're getting an output. That's an input-output model. But the problem with input-output models is the idea of blocking, right? So blocking happens when you make a request and there's another request, but wait, this request is not finished yet, and now it has to wait for the other request, right? So it's blocked. Request number 2 is blocked from modifying the the app because request 1 is in process. So what JavaScript's Node.js does is it has this thing called the event loop, okay? And this is what the event loop looks like. The event loop consists of 3 different modules. You have your call stack, you have the Node APIs, and you have your callback queue. And great, 2 years for the audio, awesome. And also attention mechanisms. I know you guys want attention mechanisms. I need to make a dedicated video about attention. That's coming. You can't just be like, oh, this is attention, but, and then that's it. No, attention is a highly interesting topic. It's an advanced topic, and we will get into that. I know you guys want it. I want it too. You know how much I like attention mechanisms. But basically the idea of attention mechanisms is normally in a neural network, you have a bunch of things to choose from, right? The network has a bunch of options on what to make a prediction with, different submodules of data. And what attention does is it says, here is the most important part of that data to pay attention to, and here's what to make a prediction with. And what it comes down to is probabilities, right? What's the % likelihood that this will result in an output that is most aligned with the label that I have? And there's different methods for this. There's a whole field of study dedicated to attention mechanisms. You could dedicate 2-3 years to this. Okay, so how does machine translation work? That's Node.js. Well, before I get to machine translation, let me just finish explaining Node.js. 3 modules here: the call stack, Node APIs, and the callback queue. Okay, this is very trivial stuff. And so here's an example, right? So what happens is for these 3 functions, well, 2 functions, what happens is they are first, when you execute this code, all those functions go onto the call stack. The call stack then calls the Node APIs, right? Set timeout as a part of the Node API. And then both are placed into the callback queue. The callback queue is waiting for the call stack to be empty, and once it's empty, it's going to send one by one different functions to that call stack. And then any new functions first enter the call stack, call the Node APIs, then go to the callback queue, and then they're executed in the call stack again. So it's kind of this loop, right? And so what happens is, because there's this process that's happening, there's no blocking. And so what that means is you can make concurrent requests, not just one, but 1,000 requests at the same time. And because there's this loop functionality, you don't have to wait for one request to finish before starting the other one. Now on to machine translation. Here is our input data and our output data, okay? So what this is, let's look at our data set, by the way. Our data set is an input-output data set example, LSTM sequence to sequence, French data. This is a very popular data set. And there's a great tutorial for this on the Keras blog as well. Mine is going to be more interactive, but let's see where the input data is. Here it is. Okay, so that's really what I want. And plus ours is going to be in JavaScript, not in Python. So this is our input data, okay? And this website has a bunch of great data sets for every language. So a bunch of phrases like hello, how are you, with the associated other language that it's translated to. I'm also going to be taking questions. So in 5 minutes from now, I'm going to be taking questions. So be sure to ask those questions before I start coding. Okay, so what we're going to do is we're going to translate English to French. Okay, so we downloaded an English-French pair. So the input looks like this left column right here. The output looks like this right column right here. And what we want to do is learn the mapping. Exactly. We want to learn the mapping between the two. And so the first step for us is to pre-process this data. So what it's going to look like is this. It's going to be a set of word vectors. And here's what the first word vector will look like. Go becomes G-O period. That's it. And this is going to be an array where every element in the array is a different character that's a part of that phrase. And the output will be the same. Great. Okay, so now for the encoder-decoder architecture, here's how it works. We have 2 recurrent networks. Okay, we have one recurrent network we call the encoder. We have another recurrent neural network called the decoder. So there's 2 neural networks here. One acts as what's called the encoder and the other as the decoder. The encoder is responsible for outputting a fixed length encoding of the input English sentence. So recurrent networks are a type of neural network that are fed not just a new data point in the next time step, right? So Feed-forward networks are fed new data points every time step, right? So here's one data point, here's the next data point, here's the next data point, and every time step, that hidden weight matrix, that is the neural network's brain, essentially. It's all of its learnings over time. It's a collection of numbers, right? Ones and zeros that gets better and better through the optimization process. For normal feed-forward neural networks, you're just feeding in input data, and that weight matrix for the network is kind of like Play-Doh. It's being molded over time to be more and more optimized, right? So it's becoming better and better. So when you feed it a new output, it's going to give you the perfect. When you feed it a new input, it's going to give you the perfect output. But recurrent networks are not just fed in new input data. So it's not just new data points. It's also the previous hidden state. So it's the previous version of that Play-Doh weight matrix. So it's being fed both of those. And the reason for that is because recurrent networks are made for learning sequences. Now, it does very well with learning sequences, right? So predicting the next character, the next number, the next image, the next frame in a sequence of images video. It does very well at predicting sequences. The problem is that there is a problem with learning long-term memory, right? So it forgets what happens in the past. Now, I have some great videos on LSTM networks. This problem is called the vanishing gradient problem, and we can talk about it forever. But basically, TLDR, just search LSTM Siraj for videos on that. But the idea is that the gradient vanishes slowly as we backpropagate into previous layers. And so there's a version of the recurrent network the version of the recurrent network is called an LSTM network. Okay, so a long short-term memory network. And here's what it looks like. And let's talk about this for a second because it's very interesting. In addition to having a hidden state, this LSTM recurrent network has a cell state. And here's what a cell looks like. Now remember, these words, gates, cells, these are just ways for us to understand what this actually is. And what this actually is a series of operations that we are applying to input data. And so we have what's called an input gate, a forget gate, and an output gate, and a cell state. We have 4 different things to be thinking about here when we're thinking about an LSTM cell. And the whole idea behind this is to trap that gradient over the long term. And this scheme has resulted in us being able to trap that gradient in earlier layers of the network such that it can remember long-term sequences. So if you look at these gating variables here, these 3 equations, if we look at these 3 equations, all right, and I'm going to answer questions right after this. Let me just finish this. If we look at these 3 equations, we have an equation for the forget gate, the input gate, and the output gate. And it's input times weight, add a bias, and then the parentheses, activate. Remember, input times weight, add a bias, activate. These gates are just single layer neural networks, right? They are perceptrons, where we're taking the input, multiplying it by its own respective weight matrix, adding a bias value, and taking that output. And what we do with all 3 of these gates is we compute the cell state. So look at this equation right here. Okay, what this equation is when we are taking all of those gates and we're going to take the first equation, multiply it by the cell state from the previous time step plus the input gate times the cell state, and that gives us our cell state. And then we take our output times tan h, the activation of the cell state, and that gives us our hidden state. So these 2 variables right here, and this is our cell state from the last time step. These 2 variables right here are what we care about, and that's what the LSTM computes. So when it comes to training, here's how it works. Okay, so here is how it works. Let me just say how it works, and then we're good with this. Okay, so what's happening is so during the training phase, we take our input sentence. This is an English sentence. Okay, we take that English sentence and we feed it into the encoder. So this is a vectorized version of the English sentence. We feed it to the first encoder, the encoder. That's an LSTM network. Now, what we care about is not the output. We care about the learned hidden state from the encoder. And what that hidden state is, we can call it a lot of things. We could call it a Play-Doh weight matrix. We can call it a hidden state. We can call it a thought vector. We can call it a learning. We can call it it's what it's learned. It's a dense representation. It's a compressed version of everything that it's learned over time, a generalized version. And we use that learned hidden state from each iteration of the training loop to initialize the decoder. So that hidden state that's learned from the encoder is used to initialize the decoder. What the decoder is fed is the French sentence. So the English sentence, check this out, you got to listen to this. The English sentence is given to the encoder. The encoder will output a hidden state. It will have an output, but we don't care about that. We only care about the hidden state that it's learned. We feed the hidden state to the decoder now to initialize it, and we feed the decoder the French sentence. So what's going to happen is the decoder is going to translate the French sentence using the learned hidden state from the encoder, character by character. It's going to predict every next character given that input. Now, it's going to output something that looks very bad at first, but we have the label, which is the actual French phrase. We'll compare it via some loss function. We'll use that to backpropagate the gradient across both networks, and we repeat until eventually the output is going to be very, very similar to the input, which is our translated phrase. That's for training, and then lastly for inference, we're going to encode the input sequence, retrieve that state, use it for the decoder, and then we don't give it a French phrase. We just immediately we predict every next character because we don't have a label. Okay, so now for questions, 5 questions, and then I'll get to the code. We have a lot of great code for you, so don't even worry about that. Okay, so question 1. How is it great for linear algebra? Linear algebra is the study of algebra applied to groups of numbers, right? So normally you're multiplying single numbers, 4 times 5, 5 times 5, and you're applying operations to single numbers. But when you have groups of numbers, matrices, which are what neural networks use, that are run on GPUs that can do massive parallel computation, you need a new type of math to be able to apply operations to groups of numbers at the same time. And that's why linear algebra, that's what it does, and that's why it's important for neural networks. Question 2, when is the School of AI starting? It's starting right now. Question 3, and the first course is going to start in a few weeks. So question 3, what are the benefits of RNN with LSTM over RNN with GRU? GRU is actually used more often now, but I think LSTMs are easier to understand. Lastly, is the app similar to Google Translator? Yes. Well, I mean, Google Translate uses an encoder-decoder architecture. It's very different than this one now because it's been iterated over time, but it's essentially the same idea of encoder and decoder architecture. One more question. Can you explain how data is formatted and how it will be fed in? Yes. Data is going to be formatted as an input vector, right, where every character is its own element in that vector or array. And then we're going to feed that in. Okay, so now let's get into the code here. What do we got here? What time are we at? Okay, cool. All right, so cool. Okay, where do we begin here? So if we go to Node.js, what we can do is we can go to Node.js.org. We can go to downloads. And we can say, what type of operating system do we have? I have a Mac, so I'll click on that, and that's going to install Node.js using a visual manager. Okay, it's a visual package manager. Once we have that, if you just joined, you haven't missed the code part yet, so that's the good part. The code is going to be in the video description, by the way, so definitely click on that. So inside of Node.js, we can download this. We can say, let's look in the docs here. Well, how do we get started with this, right? Node.js looks hard. Well, guides are usually the best place to look in any kind of technical documentation. Inside of the Getting Started guide, here's how we do it. We create a simple Sublime file or a simple text file. We paste this in, and then we hit app, and we name it app.js, and then we, in the command line, type in node app.js, and at localhost 3000, we'll see the message, hello world. That's how you install Node.js. So what I'm going to do is I'm going to get right into the meat of this code that we're going to use. It's going to be beautiful. And we got to start somewhere. So I'm going to write out this encoder decoder architecture for ourselves, for us, and then we're going to start coding it. Okay, so beautiful. So once we've installed TensorFlow.js, so npm install TensorFlow.js, we can import it, right? So there's several ways to be importing TensorFlow.js, but what I'm going to do is I'm going to import it using npm, which is the Node package manager. Now, there's also another package manager you should know about, Yarn, which is just as good, if not better than npm, that Facebook created because they were having problems with npm. Okay, and they tried everything really, but they were still having problems. And at the scale of Facebook, of course you're going to have problems. Right, so now we're going to load the pre-trained model. So this class file will contain the pre-trained model for us that we can use later on. What else are we going to import? We also have some basic DOM elements that I've written out in a separate file that we're going to look at, but that's really it. TensorFlow.js is like our main file here, and then we're going to talk about the other things. Okay, so now let's load our pre-trained models as well. So we're going to have some pre-trained models. We're still going to build models, but I just want to load them. So we have both options, right? So we could load our pre-trained models, or we can just. Okay, cool. I just wanted to see what people are saying. We can download pre-trained models, or we can have it from the web, or download it from the web. So I'm going to download it from the web. I think it's called. Where's the? What were these APIs called? What was this website called? Oh, here we go. That's what it was called. So so Google has this pre-trained model on the web for us as a JSON file. So these models are saved as JSON files, but it's not just the model. There's also metadata, right? So metadata includes things like versioning information, timestamps, things like that. Everything that's around the model, but it's not necessarily the model. Okay, so we're going to initialize this as a constant file. These are our hosted model URLs, so we can load pre-trained models. We'll also build the models, so don't even worry about it, okay? So we've got that. Great. Now we have our trained model. We have our hosted URLs. Now we can create our translator class. So now let's build the translator, okay? So here's how we do this. We define a class called translator. Inside of the translator class, we're going to initialize it, and we're going to use the async function because we don't want to wait for the DOM elements to load when we initialize our class file. Now we're going to initialize it using the URLs that we are provided. We will build our own models for sure. Now I'm going to initialize that URLs file as our own variable. I'm going to say, well, here's our model, and we're going to wait for it to load using the await function, and I'm going to have a function for load the hosted pre-trained model using the urls.model, okay? And we have that, okay? So that is our model right there. What it does, the await function, by the way, it just expresses, that expression just, it causes the async function to pause until this function that it's awaiting has loaded. So that's why we did that. Now we're going to do the same thing using the await method for the metadata, right? Because we have metadata as well. It's not just the model itself, we have the metadata. And this model actually consists of two parts. We have our, remember, we have our encoder, so we're going to call it prepare encoder model. And it has our decoder. And in these functions that I'm defining right here, we're going to segment out this model and then prepare both of them. And I'll return this at the very end. That's our initialization function for our translator class. Okay, so let's start off with the metadata because, right, it's not just the model that we're loading, it's the metadata as well. We have two different things to be loading here. Let me also see. Hi, everybody. Okay, I just want to see what everybody's saying. Cool, cool. We have people joining in. We have people leaving. Don't leave. Stay. stay, okay? This is important stuff. This is more important than web development in general. Look, machine learning is the future of all code, okay? Everything's gonna be machine learning. And if you want to stay on top of things, you need to understand how this works. Starting with metadata, okay? So back to metadata. Back to metadata. Where were we? So we can retrieve this metadata from our helper class, because we have a helper class here. And we're going to use the loader. Remember, I imported that loader at the very beginning. Load hosted metadata using the URL's metadata. Okay, so that's the loader. That's our translation metadata. Now we can say, well, let's take our decoder. And so now we're going to retrieve some things from the metadata. So remember, we're retrieving what already exists. So we can say, well, we know that one of the variables of the metadata, and if we look into TensorFlow docs, it has these features. But one of the variables of the input data, or of the metadata, is the max sequence length for both the encoder and the decoder. Okay, let me zoom out a bit so people can see what we're talking about here. There we go. Now we have the same thing for our encoder. So we have a max decoder length, we have a max encoder length. And again, we can use that same model to retrieve that. And it's going to look very similar, except it's going to be called the encoder. Yes, you're right. Cool. Max encoder sequence length, right? Okay, yes. So now we have our decoder, or we have our encoder sequence length, and now there's actually const, yes. So const needs to be, let's see, translation metadata. Oh, right. Thanks. Right. There we go. Thank you. Right, yes. Thank you, guys. This is how we do it. Crowdsourced debugging. So now back to this. So we have a token index as well. Now the reason we're going to use this token index is so we have a way of knowing where in the phrase we are when we are predicting the next character in the sequence. We need a way to predict where we are, and so the metadata has that, and it's called the input token index. Now we have that not just for the input, but we have this for the target index. Now what the target index is it's the final label that we are trying to predict, right? So that label is the output French phrase, okay? So that's our index. Now that's it for metadata. Now I want to prepare the encoder model. Prepare encoder model, okay? And it's going to take the model as its input. So it's going to segment out the encoder model using the pre-trained weights. And we can train it on our own data, right? So it's already been trained on language pairs, but we can just train it ourselves. We can just add training to it, right? And also, this is the future of machine learning, where you don't necessarily have to train your own model from scratch every time, because someone else has done that. In the same way that you don't have to write code, right? You don't have to write all the bare bones code for everything every time. Someone has already done that. So you import a library. So the paradigm that we're going to start seeing with machine learning is one where we are not just importing libraries, we are importing pre-trained models. And not just single models, but multiple models trained on multiple different types of data. And we can combine all of these models together and then train it on our own data. And we won't need as much data because of it. It's a much more efficient process. Now, enough of that, and let's get back to this. Okay, so back to the encoder model. So what does this look like? So how many encoder token count? How many encoder tokens do we have, right? So what these tokens are the number of characters that we are inputting into the encoder. And what we can do is we could say, for the length of this, and it's going to be of size of shape 2 because there are 3 different 0, 1, 2. So those are the elements in the array. There are 3 different words in a phrase. And we can say that's going to be the number of tokens. Now we have to decide, well, how many inputs is going to be in this? And we can use the equal sign. We could say, well, model.input 0. That's going to be the input to the model. Now remember, we are using the hidden states as the medium with which to initialize a decoder. So we need to retrieve both of those. So we have our hidden state, state H, which we're going to retrieve from the models, and we're going to say, well, here's a specific layer where it's at. But it's not enough to just say we need the hidden state. We also need to have that cell state. So recall, I just talked about LSTM networks, and what LSTM networks do is they don't just offer hidden states, they offer cell states. That's what's learned. And what does that prevent? That prevents the vanishing gradient problem. And what does that do? That lets us learn long-term sequences, okay? So that's our hidden state, that's our cell state. And what we can do is we can say, well, let's create a new list and put those values into this single list that we've just defined. And we'll take that list and we'll use it to build the model, okay? I see it. Translation metadata, input token index. It is, right? Translation metadata. Yes, I will use the semicolon consistently. We got some JavaScript people in here, which is good. It's not just all Python people. We want diversity. We want variety, guys. Okay? JavaScript, Python. Look, Python is obviously where it's at for machine learning. And this is kind of controversial to say, but if I were to pick a number 2 language for machine learning, I'm going to pick JavaScript. Not R, not Scala, not Go, not MATLAB for sure. But it's JavaScript. And there's a lot of reasons for that, but there's a lot of developer activity around JavaScript libraries for machine learning. And I have a great video on that coming out this weekend, by the way. So now we can build the model. So now we're actually using a TensorFlow.js function, tf.model, to build this thing. And we can say, well, here are our inputs and here are our outputs. Our outputs are going to be the states, right? Because we want those states to be fed into the decoder. So that's what we're outputting. Okay, so that's us preparing our encoder. And now let's prepare the decoder. Prepare decoder model using the same, remember, we are segmenting out this model. Oh, I see. You're right. Yes, that's what you meant. Okay, I just want to fix some syntax here, and now we're back. Thank you. So prepare decoder model looks like this. So again, we are going to do the same kind of basic idea where we are deciding what we are trying to see what the number of decoder tokens are going to be. So we'll say num decoder tokens, and it's going to be model.input1.shape. And then we're going to say, well, okay, so let's define our hidden state. So we have our constant, our hidden state, and that hidden state is going to be just that. Again, we have our hidden state. Now, what we need to do is define a latent dimension. Now, the reason we are defining this latent dimension using the hidden state is it's going to help us define the input. Now, let me talk about what exactly I mean by that. So it's going to be 1 less than the hidden state's size or length, because how many live people do we have, by the way? Constant latent dimension. Cool, cool, cool. All right, so we're going to use this latent dimension to help us define the inputs directly into both hidden states. So let me show you what I mean. So I have a decoder state input H. I have a decoder state input C, which is the cell state. And then I have a decoder state inputs variable. Okay, so these are our three variables.
You're missing an equal sign of 54.
Thank you. Okay, thank you. All right. Now we're going to actually use some TensorFlow.js input functions. One is going to be tf.input shape using the latent dimension. So here is why we use the latent dimension. We are using the shape of the hidden states -1 to define the decoder state's hidden state. Okay, so it's going to be -1 because we are predicting the next character in a sequence, right? It's not the, it's going to be the, if the input sequence is t, we're predicting t +1, so the next one. So the input shape has to start 1 before. Line 67, thank you. Latent dimension is the shape. We have our name, which is going to be decoder state input H. Okay, and now let's do the same thing. Let's make this a little smaller so we can all see this. Let's do the same thing for the cell state, and we'll do the same thing. Now, these are our inputs. Now that we've defined both of them, now we can say, well, here's our input H, and here's our input C. Now, these are our state inputs, right? So these are our hidden states, and this is our hidden state and our cell state. Okay. Now that we have both of them, now let's retrieve the LSTM model, just like that. Okay, so I just want to take a little break to say, Juan Luis Clore said, how do you convince the public we really live in the machine learning era? Well, it's too hard for a country like Bolivia in South America to believe in that. I don't care where you live. You can live in Antarctica. As long as you have an internet connection and some kind of computing device, this could be $100, convert to your local currency, Chromebook. As long as you can access, let me show you this, collab.research.google.com. Okay, you go to this in your browser, okay? This could even be Internet Explorer, like the worst browser ever. But as long as you have a browser, you create a notebook. You say, hello world, in that notebook. You hit this. It's compiling it on an NVIDIA K80 GPU. You have 12 hours of training time on this thing for free. It compiled it on that and it printed it out. You have everything. You have your algorithms, okay? That's all available on machine learning subreddit. It's available on tutorials online. You have the data. It's all available using awesome GitHub public lists, Reddit r/datasets. You have the education, me, other YouTubers. You have the compute here. So I don't want to hear, I live in South America, Bolivia, whatever, I can't do machine learning. I don't care where you are. Here, you can do this. So don't ever give me an excuse like that again, all right? So that's enough of that. IE will be suing me. No, actually, Microsoft asked me to make an Azure video, and I said no. So let's see them sue me again, all right? So here we go, back to this. Where was I? I got a little off track. I got a little passionate about that.
Line 70.
Thank you. Back to the...
Something about a variable name.
Right. Thank you. Okay, so on line 70, we have our tf.input. What went on here? Yeah. Interesting. Looks fine to me. tf.input h. Okay, so back to the retrieving the LSTM model. So we can say, well, here's our decoder, and we already have our decoder. We're gonna take that last layer of the decoder LSTM, Oh, I see. Capital L. There is no capital L. Okay. So back to this. We're going to define our initial input by saying all those layers going to their decoder LSTM.
Capital I instead of.
Oh, I see.
Okay.
Thank you. Capital I. Here we go. Ah, gotcha. Got it. Cool. All right, cool. So now, input, capital, great. Please zoom. Guys, how much zooming do you want here? Okay, here we go. Decoder state.lcm input 0. So this is our initial input. Okay, this is our initial input. And now we can initialize the model using the first input and the hidden states input, which we've already defined here. So we can say apply outputs equals decoder LSTM. How much time has passed so far? Decoder, thanks. No, I mean like how long has this stream been? Decoder inputs. State, decoder, state. Cool, thanks. All right, that's our outputs. All right, I have about 10 more lines of code here, so stick around. I have 10 more lines of code, and I'm going to answer some questions at the very end. Okay, I'm going to answer some questions, so don't go anywhere. Back to this. Decoder states inputs, right? So now I have those outputs. So what we want to do is we want to get that last output. It hasn't been activated yet. We haven't applied a dense, fully connected layer to it. So we have both of our hidden states, by the way. We have both of them already, both the hidden states and the cell states. And what we can do is we can just say, let's take the first element of this apply outputs array or list and store that in the decoder's hidden states. And we'll do the same thing for the cell state, and that's just going to be the next one. And then we have our hidden, so these hidden states are going to get their own list. Now that we finally retrieve these hidden states, we can give them their own list. And so these alone aren't going to do anything. We have to apply a fully connected layer to them. What this is going to do is it's going to output a probability value. Why do we want a probability value? That's what the dense layer is. Because a probability value will allow us to make a prediction on what character is the most probable next character, right? So if it's going to say, 70%, H, then it's very likely going to be H as the next character. And that's why we apply a dense layer to it. So to get that final output, we're going to use that dense layer to define that output. We have our decoder model. All right, so that's our final output. We applied the dense layer to the output, and now we have a prediction. Okay, so the decoder model is going to use its own TF model. And it's going to use as input the decoder's inputs concatenated with the states, the state inputs.
Check line 80 for outputs. You're missing a T.
Thank you. And we have our outputs, which are the decoder outputs. Okay, that's it for this little portion of code bits. Okay. Let's review what I've written here, by the way. Okay, let's review this. So, line 87, right? There we go. Making sure I got all my... I still haven't registered Sublime Text. At this point, it's just become a meme. Like, I will never register Sublime Text because I don't know why. Sublime better like sponsor me or something. I don't care. No, don't worry about it. I love you, Sublime. I don't know why. I just don't want to. I like being a rebel. Back to this. I have my friend Oz Balabanian who is helping me live stream. That's who's sitting next to me. So he's helping me with this live stream stuff, okay? He's got a VR channel. Back to this. Okay, so let's just go. Anybody can go to TFJS examples, and here are all of these examples, by the way. You have your cart poll, all right? This balances a cart poll in the browser, and it's got a live demo. Most of them have live demos in the browser that you can see if you just click see the example live. I want you to for sure go to this GitHub repository if you haven't yet. Look at this thing, training in the browser. Okay, and so what I'm gonna do, I'm gonna download this right now. Let me download it. Let me click open. Let me go to it. Terminal. Let me go into it. Make this bigger. Now let's run this ourselves. So cd translation, and then I'm gonna answer some questions right after I run this demo. Okay, so if we go here, let's look at this. What does it say? Translation. Okay, it says to do two things, yarn and yarn watch. So yarn, I can do that. So what yarn is it's a version of NPM that Facebook created, remember? That bypasses a lot of the issues with NPM at scale. And so once we've run yarn, now we can run yarn watch. And what yarn watch is going to do is in the browser at our local host, it's going to run that pre-trained model. Okay, at localhost 1234. Now it's going to show up here. Okay, that's the whole point, is that it needs to show up. Now we're going to load that pre-trained model, and we're going to go ahead and say, you are cool. Tu es malin. That's my French right there. Omelette de fromage. Omelette de fromage. Okay. Question time. So just ask questions. I'm reading all of this in real time. Let's answer some questions here. Link to everything is going to be in the video description. Definitely check out collab.research.google.com. Check out the GitHub repository for Tensorflow.js. I love you. The School of AI first course will start in a few weeks. I have big things planned for everybody. It's a very exciting time right now. And Yarn does not come with Hadoop. However, you can use Yarn with Hadoop. Why use a different activation function, H, in one place? That's a great question. So check out my video, which activation function should I use, Siraj? Just Google that. Any advantage of Node.js over Python R? Yes, one example is the ability to easily use distributed computing, right? So client-side machine learning involves using the GPUs of whoever the host is. And if we use client-side machine learning with JavaScript, you can train it on their GPUs in real time. Now, you could do this with Python using Django and Flask, but it's much easier with JavaScript. 3 more questions. How can I make a related word to a specific topic AI? Okay. Word2Vec, Google that, YouTube that, Word2Vec Siraj. But you turn words into vectors, and then you can find the similarity between these vectors. It's a numerical operation. And Rivan says, I'm the cutest, I'm sure. And Passionate says, deep learning with Django. It's not a question. Last question. Okay, the last question is Vishal. Vishal asks, can you suggest some good books for linear algebra with regard to machine learning? No. I'm not going to suggest good books. Why? Because you can very easily learn linear algebra from 3 blue, 1 brown. Okay? If you just search linear algebra, my buddy Grant here, promoting him right now. Essence of linear algebra. Definitely check out this series. Amazing playlist. This is enough. Watch all of this, then watch Math of Intelligence by me. If I do say so myself, an amazing playlist. Okay, this is when I was in Europe. I was just like going through that. I was just so hyped. You know what I'm saying? Like I was totally in the zone. I was combining art and music and like everything together with machine learning. It was sick. Now I have to outdo that with my first School of AI course, and I will. But that's that question. Okay, so anyway, I love you too. Look, you guys don't need to qualify I'm not gay, okay? Even if you are gay, that's fine. Who cares? Okay? People are gay. That's humans. But I love you too. It's okay for us to be able to say I love you as men, as women, whatever. Okay, we are beyond gender roles, by the way. You guys, listen, we are moving beyond being a human. We're moving beyond these bodies, period. So forget about gender roles. We are merging into this super intelligent civilization using AI. So don't even trip about like, I'm not gay. I love you, by the way. And lastly, will it be free? Of course, it's going to be free. Yes, it's going to be free. And I have so much content coming out for you this weekend. It's going to blow your mind. We are living in such an exciting time right now. Next week, we're going to have our first School of AI meetup starting. I'm going to contact all the people who I've selected to be deans. It's going to be amazing. You guys are amazing. This is the most important community in the world. Nobody, as a community globally, is doing as much in terms of impact. And do you know why? Because nobody's using AI as much as we are. We are the most AI aware, active, hungry, ambitious community in the world. And it's all thanks to you guys, all right? So that's it for this. I'm not gonna wrap because it's kind of laggy right now, but I will wrap, I promise you, in the next live stream, okay? So lots of wraps are coming. I love you guys, and thanks for watching.